All right, let's get into it. Today we are talking about one of the most powerful concepts in high-performance databases. And I'm not talking about a simple tune-up. This is a full-on engine swap.
Welcome to day 24. That's right. Yesterday, we built our Bloom filter, our bouncer, to keep all the bogus requests out. Well, today, we're taking that database it was protecting, and we're throwing the whole thing in the trash. We're going to build something way, way faster.
Okay, so let's start by identifying the villain of our story. It's called the random write, and it's pretty much the single biggest reason why most databases feel so slow.
So why is that? I mean, why does something as simple as saving data bring these massive systems to a crawl? Well, it all comes down to the physics of how hard drives actually work.
Let me hit you with a quick reality check. You might imagine saving data as this neat, orderly thing, but what's really happening inside a traditional database, it's just pure chaos.
Okay, picture a giant spinning metal disk, like an old record player. To update just one piece of data, a little robotic arm has to physically jump to a spot, make a tiny change, then frantically jump to a whole other spot to make another change. It's just jumping all over the place. This is called random I/O, that's input-output, and it is the absolute enemy of speed. Hard drives hate doing this.
But what if we could just stop jumping around? What if there was a way to write data that hard drives actually, love to do? Well, there is, and it's a surprisingly simple trick.
So here's the secret. Instead of writing randomly, what if we just wrote everything in one long, continuous line, like drawing a single, unbroken stroke with a pen? This is called a sequential write, and it is, bar none, the fastest thing a physical disk can possibly do. End of story.
And this leads us to the core concept, the append-only log. It's exactly what it sounds like. It's a file where you only ever add new stuff to the end. You never go back and change anything in the middle. And that simple rule makes everything from recovering from a crash to dealing with a ton of users at once so much simpler and faster.
And look, this isn't some weird theoretical idea. Remember Cassandra from back on day 19, the database built to handle just insane amounts of data? It's powered by this exact philosophy. This is how it survives getting hit with massive data dumps. All right, so we're sold. We're only going to write sequentially. But how do you actually build a system that can do that, especially when requests are coming in totally out of order? This is where we build the engine, the log-structured merge tree, or LSM tree. Let's meet its two most important parts, memtables and stables. And here is where it gets really, really cool. To get this crazy speed when a write comes in, it doesn't even go to that slow spinning disk. Nope, it goes somewhere much, much faster. So plot twist, we're going to use memory. Picture this, an incoming write comes in. Instead of hitting the disk, it gets caught in a glowing bucket made of pure RAM. We call this our memtable. Inside this bucket, the data is instantly sorted on the fly. Then, once the bucket is full, the whole thing instantly freezes into a perfect, glowing, unbreakable brick and just slides onto the disk as a new file. That brick is our SS table. It's a beautiful, zero-friction process. And that glowing brick, it has a formal name, an SS table, which stands for Sorted String Table. It's a file of key value pairs all perfectly sorted. And the number one rule of SS tables? It is immutable. Once that brick is made, you never, ever change it. And this diagram shows you how it works in the real world. A write comes in and goes to two places at the same time. First, it hits a commit log on disk. That's for safety. So if the power goes out, we don't lose anything. But it also goes into that super fast memory cache, our memtable. When the cache fills up, boom, it gets flushed to disk as a brand new SS table. You get speed from memory and safety from the disk. Best of both worlds. So we've solved for ridiculously fast writes. But we've kind of created a new puzzle for ourselves. With all these little files piling up everywhere, how on earth do we find anything? I mean, this is the critical question. If the latest version of my data could be in the RAM bucket, or maybe in the newest brick we just made, or one of the hundreds of older bricks, how would we find it without searching forever? Well, the process is pretty logical, but it sounds kinda slow at first. First, you check the fastest place, the memtable in RAM. Not there? Okay, check the newest SS table on disk. Still not there? Check the next oldest one, and the one before that, and so on. You can see how this could take a really long time, right? And this is where our bouncer from yesterday saves the day. The Bloom filter isn't just for the front door. We have one for every single SS table file, and it can tell us instantly if a key is definitely not in that file, so we don't even have to waste time opening it up to look. Let's trace it. A read request comes in. First, check the memory cache. Nothing. Okay, now, instead of looking at every single SS table, we just ask the Bloom filters. They're like our map. They instantly tell us to ignore all these other files and point us to the one SS table that might have our key. We go straight there, grab the data, and we're done. It's a huge shortcut. So, after all that complex work, what's the big payoff? And of course, what's the next problem? The payoff is just breathtaking write speed. By turning those messy random writes into clean, sequential ones, this whole architecture, the LSM tree, can handle millions of writes per second. This isn't just theory, it's how the biggest tech companies in the world ingest all their data. But this, of course, leads to our next challenge. Our system is fast, but it makes a lot of files. What happens when our server floor is covered in 10,000 of these glowing data bricks? Our reads are going to get slow again, and we're going to be wasting a ton of space.
So, what do we do about those 10,000 glowing bricks piling up and slowing us down? Well, tomorrow, on day 25, we're going to clean up the mess with a process called compaction, and we'll meet the legendary B tree. You are not going to want to miss it. Make sure you hit subscribe.